Good day, ladies and gentlemen. This is our lecture number 3 on Cmen846. Today we are going to be looking at cathode ray tube displays, which we call CRTs. And as we all know, the cathode ray tubes have been in existence for a very long time, though their existence is being replaced by flat screens, both in oscilloscope, in television, in computer screen. They have been replaced by flat screen, but nevertheless the syllabus of this course do include them, therefore we have to discuss them. What these cathode ray tubes do is they produce a dynamic and quality high information content image at a very high resolution. And of course this cathode ray tube is available using, with different size of the screen, diagonal size, ranging from 12 mm to 1 meter or even above that. And of course they have resolutions ranging from thousands of pixels to more than 5 million pixels per a single frame. And of course the image is formed on the CRT following these 4 stages. The first one is the beam formation, the second one is the beam focusing, the next one is the beam deflection, and finally the energy combustion. And these 4 stages, they take place at 4 different regions in the CRT, starting from the rear, that is the most backward part, which we call the electron gun, down to the first plate where the image is incidented and formed. Now, this is the diagram of a typical cathode ray tube, and as you can see, at the extreme left, we have what we call the heater coils. They are the ones for heating, used for heating the cathodes, and surrounding these coils is the cathode. That's our negative electrode terminal. And following that, we have electromagnetic focusing lenses on both sides, above and below. You can see that we have Q1 and Q2. We are going to discuss on them in more detail. And of course, if you look at it, after that, as you progress to the right hand side, we have our horizontal and the vertical deflection coils. And after them, we have our anodes. Then everything now proceeds to the most front part at the right hand side, where we have our first plates, which is made of phosphor coating, and it is on these plates that the image is formed. Now let us start looking at these 4 stages of forming image by CRT. The first one is the beam generation, as we have seen, and it is being done using what we call electron gun. Now, how does that happen? Our cathode is actually a metal. As you know, in a battery we have cathode and anode, cathode being the negative and the anode being the positive. So this cathode is made of metals. Typically a nickel is used, and of course this nickel is coated, that is electroplated with a thin layer of oxide of some element. Also, the most typical one is barium strontium compound, which the oxide of this is used for plating the cathodes, which is the nickel in this case. And if you want to produce the voltage for the electron emission, definitely you have to make sure that the value of the requirements of that voltage is reduced. And how do we achieve that? We achieve it by heating our cathode, ranging from temperature of 700 to 1000 degrees Celsius. Now, if you want to have a high brightness application, then you have to use more advanced and more expensive dispensers. That is the ones that can give you more discharge of electrons at very low voltage, and of course even low temperature. And the cathodes are designed in such a way that we increase the current or the beam current with long cathode life. That is to make sure that the beam of electrons being produced, they are large in number, and of course the lifespan of the cathode also without degrading should be long. And if you do want to do that, definitely your design approach has to change, and of course the expenses for achieving that is very high. Now let us look at the flow of electrons from the cathode and how it is being controlled. And this control is done by varying the potential between the cathode and the series of what we call the control grids. As you can see from that diagram, we have G1 and G2 inside the electron gun, if you pay attention. So the G1 is used for controlling the flow of the electrons. That's why we call it control grid. And the G2 is for accelerating the electrons produced towards the first plate where the image is formed. Now the voltage that is used is within the range of 100 to 1000 volts, which is placed between the G2 and, as you can see here, we said it is our accelerating grid. So between the G2 and the cathode, and its function is to pull away the stream of electrons that are produced by the cathode so that they can be pushed towards the point where the image is formed, that is the first plate. And the amplitude of this beam is controlled by varying the potential on G1, and that is why I said G1 is called the control grid. Now the voltage that is applied at this G1, its function is to control the brightness, because the brightness is directly proportional to the beam of current. So we use the voltage at G1 to control the brightness. And if we use the electron optics, this beam spot is imaged, that is formed on the first plate, which is phosphor screen. And this approach has inherent, that is inbuilt advantages. So the crossover design is the one that is used because it has very much higher advantages compared to the other approaches. So this crossover beam is narrow in nature so that it will be more focused. So it is easier for it to be deflected to the point where we want the image to be formed, and of course it will improve the resolution of the final image that is normally formed. Now that is about the beam generation. Now we come to the second stage of 4, that is the beam focusing. And this beam focusing of electrons is just comparable to the focusing of beam of light, because whenever there is a light coming from source, you can either diverse it or you can converge it. So focusing has to do with converging to a particular selected stage. And these CRTs, their size, as I told you, even the screen size from millimeters up to 1 meter or above 1 meter. So as they become larger, then they operate at higher deflection angles. Therefore, there is a critical need for controlling the spot. That's the place where the image will be formed. And this focusing is achieved using 2 approaches. One is electrostatic focusing grids, and the other one is electromagnetic focusing coils. The first one is grid, and the second one is coil. The electrostatic focus is the most commonly used technique in the CRT application, and it is the one that has been used in television screens and of course the desktop computer monitors that are CRT in nature. They use electrostatic focusing, and this electrostatic focusing is achieved by first applying a level, that is association of potentials, that is different levels of voltages across the focusing grid. And it has a complex sequence, that is arrangement of focusing grid, which are built into the electron gun. The next item is on electronic or electron beam deflection. And to deflect an electron beam, it is just to control it in such a way that you can drive it from the source up to the front face on which the image is formed. And this beam deflection techniques is divided also into 2. We have electromagnetic and we have electrostatic version. The electrostatic system, it has 2 electromagnetic yokes. If we say yoke, is nothing but just like a rod that has two ends, and these yokes are placed on the opposite sides of the neck of the CRT, as we have seen here. Let me go back to the diagram. Look at it. We have this, the ones at the neck, they are our yokes, and one of them is used for horizontal deflection and the other one is for vertical deflection. And the position of the beam should be controlled in such a way that it can easily be directed to the front face of the CRT where the image will be formed. And the amount of this deflection created for the beam is directly proportional to the amount of current in the coil. And the more we consume current, definitely the more the quality of the system deteriorates. So therefore, in this case, you have to strike a balance in such a way that you increase the current to BRS minimum in such a way that it will not cause degradation of the system. And the CRTs that needs a moderate or high resolution, they use magnetic deflection technique. And the reason is because it is low cost and of course it has a very good efficiency. The electrostatic deflection version, on the other hand, it is faster than the magnetic deflection, but it is less in the spot of size control. That is, you have to put more energy and concentration before you can control the spot size that will be formed on the front screen. And this one is typically used in oscilloscope, whereas the other one, as we have said, they are used in what? In a system where they need very high or a moderate resolution. So for this moderate resolution we've talked about, the most important item that is for the oscilloscope is the speed of the deflection. We need to increase the speed in such a way that within a short time the waveform captured from the electronic system can quickly be displayed on the screen of the oscilloscope. Now we have what we call CRT addressing. Addressing is nothing but a process of sending these beams generated from the electron gun and then directed to form image on the screen. How are these beams deposited on the screen? We have two methods. The first one, we call it raster scanning, and the other one is called stroke scanning. Now this raster scanning is the most commonly used now in most of the systems, and this raster scanning, the electron beams, they write each frame line by line on the screen. That is, it's finished with one row before it goes to the next one, and it starts from the upper position of the screen downwards. So in this case, since it writes horizontally, definitely the horizontal deflection we have seen, it requires higher bandwidth than the vertical deflection. The reason simply because the rows, the horizontal lines are the ones written one by one, and then you keep on going down. So for this reason, the high performance CRT, they have a horizontal bandwidth ranging from 15 kilohertz to 250 kilohertz. And if you look at this one very well, if you say 250 minus 15, it will give you a bandwidth of 235. While the vertical one, it is from 30 to 180 kilohertz. If you subtract, you are going to get only 150. So this shows that the vertical or the horizontal bandwidth is more than that of what? The vertical. And of course, in this raster addressing method, the information is written on the front of the screen from left to right. I have already said this, and from top to the bottom I have already also said that. Then this raster scanning is divided into two. We have what we call interlace, and we have what we call the progressive raster scanning, non-interlace. Now the interlace scanning, each frame is divided into two fields. The first field contains all the odd numbers, and the second field contains all the even numbers. So for this reason, whenever you want to write a field or you want to scan a field, it is scanned twice. The first scanning to take care of the odd numbers, the second one to take care of the even numbers. The commercial television screen, they are interlaced in nature, and this interlace, it has a very good name, or a popular name. It is called NTSC, and this stands for National Television Standard Committee, and the other one is called PAL, which is Phase Alternative Line. And these are the two types of interlace method. And this interlace, it has some advantages. The first one is the transmission bandwidth is conserved. The second one is electronic bandwidth is also conserved. If you say conserved, you save it from being wasted. And of course, the CRT bandwidth is conserved. So these are the advantages. And while it conserve all these three bandwidths, at the same time, the performance is very, very high with respect to the moving imagery and with respect to the resolution and the flicker. What we mean here is the fact that it conserves transmission bandwidth, electronics bandwidth, CRT bandwidth, it doesn't compromise the quality, the performance of the moving imagery, the resolution and the flicker. All of them are within the acceptable level. The computer monitors, on the other hand, they use the progressive raster scanning, and in this case, each frame is scanned only one. Unlike the interlace where we said it is scanned twice, one for the odd and the other one for the even frames. And the display in this progressive raster scanning is generated line by line. I've already explained it. It is writing horizontally from top to the bottom, and it is starting from the first pixel up to the last one using rows. Now, the second method, apart from the raster, is the stroke addressing technique, and this is the one that before it was very popular, but now it is highly diminishing. The raster is the most commonly used, and the name of this, that is the stroke scanning, it is obtained from the praise, the stroke of a pen. If you want to put a dot on a paper, you stroke it with the pen so that only one point comes out. So this stroke is a point-to-point addressing system, that is, it puts dot in every place where the information is, and the beam is directed from the starting points, that is, from the left hand most to the right. And since it is not a raster, its resolution is independent of the direction, whether it is starting from left or right, despite the fact that it starts from left to right. But whatever happens, even if you change that orientation, the resolution will not suffer anything. And the resolution is only having one problem, that is, it is limited by the spot size. The spot size is somehow not as qualitative as the raster scanning we have discussed. This stroke scanning addressing is very, very excellent whenever you have CRT that needs low information content. And of course, it has another advantage, that it gives detailed graphic characters, and of course the simple vector graphics, that is the information that will be formed on the screen. It is of the same high quality, despite the fact that it doesn't require much work as compared to the raster, where we have to scan twice. And this one, it has advantages. First one, that is high quality of drawing the image. Second one, the lines that will be formed are very clean, and the next one, the details are very precise, you see everything. And the last one, it has high speed, and at the same time it conserves the bandwidth and the power consumption. So if we ask what are the advantages of this stroke, we have 4 here. And of course, it addresses the CRT in the places where there is an information, and it will skip all those other places where there is no information. Unlike in the raster, where it will scan everything, whether there is information. Wherever there is information, it puts 1. Where there is no, it puts 0. But here, it addresses only the places where there is an information. And this technique is uncommon today, as I've already said. The reason why it is not being used most commonly, it is too slow. And of course, it is computationally intensive. That is, it consumes very large time while trying to form an image. And for this, it is not used in the systems that need high information content, because it will take longer time before the image is formed. And of course, the informations that are having what we call the grayscale are not used, because also the information is high. And of course, wherever you are dealing with the information which is having an image, something like a picture, so it will take a very long time before it can form the image. That is why it is not used these days. We now look at the Phosphor screen. This Phosphor screen is the screen on which the image is formed, and it functions in the CRT displays. It is just like a transducer. Its function is to convert the energy of the electron beam into the visible light in form of image. And this conversion of the beam energy into the light energy, it is called cathodoluminescence. And it is inorganic crystalline material, that is the phosphor itself, and it is doped with 1 or more than 1 impurities, which are called activators and co-activators. And this phosphor, as we said, it is the part that emit light. It does that in 2 ways. We have what we call fluorescence, and we have what we call phosphorescence. What is the fluorescence? It is simply the ability of the phosphor to emit light while it is under the bombardment of the electron beam. That is, when the electron beams from the gun are directed to incident on the screen, whenever they are incidenting on that very time and it is emitting light, that is what we call fluorescence. Then the other one, it is called phosphorescence, and it is nothing but the ability of the phosphor to continue emitting the light when the bombardment of the electron beam has stopped. And the length of time it can do this phosphorescence, that is to emit light while the electron flow has stopped, is what we call the persistence. And this persistence varies, because we said it is time. It varies from nanoseconds and sometimes up to number of minutes, and in other materials up to even hours, not minutes. And the CRTs, they take advantage of the 2 ways of emitting light, that is the fluorescence and the phosphorescence. And it occurs, as I have said, when the beam of electrons are excited, that is, they are moved from the ground state energy and they move to the higher state energy, that is the excitation level inside that phosphor. And as we know this during our chemistry in the secondary school, whenever you excite an electron to move from its ground state to excited state, it will stay there only for some time, then it will release the energy and come back to its original shell or orbit. So whenever the electrons are coming back from that excitation, they will release the energy they consume and they will emit it in form of light. That is why the phosphor is able to emit light and form image. And the choice of the phosphor material, it depends on the application it will be used. And of course, there are some parameters like wavelengths, whether you are going to use it for a narrow spectra or a broadband emission. That is a factor that is considered while selecting the phosphor screen. The color, the brightness, the resolution, and of course the persistence, they are all parameters considered when selecting the type of phosphor material. The commercial television CRTs, they use the following phosphor powders. The first one is zinc sulfides plus silver plus a chlorine, and this powder will give you a blue color. And the other one is zinc, cadmium, sulfur. Then we have copper and aluminium, or zinc sulfide, copper, gold, and aluminium, and this is for the green color. The television CRTs, they use moderately short persistence phosphor. I told you the persistence starts from nanoseconds up to minutes, sometimes even up to hours. And the reason why we use short persistence phosphors for television is to make sure that the frame does not exhibit what we call blurring. The blurring is for the image to be somehow dark due to what the previous frame. So wanted to quickly stop emitting the light the moment the stream of electrons stops, so that there won't be a problem of blurring. And the possible for other applications where the screen is refreshed not frequently, then it has a mix of the two. That is the phosphor elements that have short and the ones that have long persistence. And today that we have digital systems, the use of this long persistence has declined. Majority use short persistence combination. And the color of the CRT, using what we call the shadow max. The color, you know, the previous televisions we call them black and white because they have combination of the only two colors, black and white. But with the advent of the color TV, where we can have different colors, this one started in 1950s, and this is also introduced into the CRT application, and the color is created in any CRT by using what we call a gun shadows, 3 of them. And these gun shadows, they are metals, and they are placed at a position just before the screen where the image is formed. The 3 electron guns are used, 1 gun for each of the 3 primary colors. We have red, we have green, and we have the blue. And there are 2 common configurations for this, or for arranging the guns. One is called delta, everybody knows delta, something like a triangular, and the other one is in line, which means all the 3 are arranged in a straight line with respect to the position of the atom. Now, what are the parameters do we consider for we to know the quality of the image formed by CRT? One of them is the resolution, another one is luminance, the next one is contrast, image fidelity, color, and the bandwidth. And each of these 6, they are determined by some parameters. For instance, if you take the resolution, the spot size, and the shape, the focus accuracy, the line width, the addressing technique used, all of them, they influence the resolution. The same thing for luminance, the same thing for the contrast of the bandwidth. You can read these ones and study them one after the other. Now let us look at this resolution. As we said, it is affected by almost every parameter. For instance, the size of the spot, the focus, that is how the beams are consolidated in one place so that they will form an image in one point. The deflection, the raster format you use, whether interlaced or non-interlaced, the max for the 3 colors we just discussed, the beam current, and of course this resolution. If you want to get high resolution, it is very, very difficult to achieve if at the same time you want high brightness, which means between the brightness and the resolution there must be some trade-off, that is to compromise one in order to improve the other one. Now we have what we call MTF, that is modulation transfer function, and it is a standard metric for identifying the resolution. And this resolution is also defined, or is also dependent on what we call shades of gray, which is the characteristic of the image source and of course the capability of the electronics on that test. This grayscale, as I said, it is defined as the series of steps in brightness. As you change the grayscale, you are also maneuvering the brightness until you reach the best of your choice. But I told you, resolution and the brightness are two things that cannot be achieved at the same time. There must be some trade-off. Now let us look at the CRT and the lifetime of the phosphor, that is the screen itself. This lifespan of any CRT screen, it depends on how it has been driven, that is how it has been used. The higher the beam currents incidenting on the screen, the more rapidly it will start degrading. So this degradation is due to failure of three parts of the CRT. The first one, failure of the cathode where the electrons are produced, a failure of the phosphor on which the screen is formed, and the failure of the glass, which is the external thing on which we see the image. Now, the brighter the displays, they actually require a very high amount of current, because we said when the current is very high, the coil will be heated more and they will emit more electrons, and the more the electrons, the higher the brightness. So, and this definitely requires the higher level of cathode loading. That is, whenever the current is very high, the cathode will be producing more number of electrons, therefore it is overloaded. Now, sometimes this oxide of these cathodes, they are okay to operate within the range of current from 0.1 up to 10 ampere per centimeter square. And of course, if you operate it within this range, you can have a typical lifespan for the phosphor of around 10,000 hours. And we use a technique which we call the dispenser cathode. And this dispenser cathode is another approach of designing the cathode in such a way that the lifespan can be multiplied 2 times the one without it, or even 3 times. Now, the phosphor degradation, it also affects the lifetime of the CRT and of course the performance of the CRT. All these phosphors, they degrade, that is, their quality reduces due to the electron bombardment I have already talked about. And whenever electrons are incidenting on the phosphor, they create a problem that we call phosphor burning. And the rate of this burning, that's this degradation, depends on 3 parameters. The first one is the beam current. The higher the current, the higher the degradation. The second one is anode voltage, and the last one is the material parameters specific to each phosphor, selection of the materials for manufacturing the phosphor screen. Now, we have another mechanism for degradation, and it is called the glass browning. That is the external glass on which we see the image. It has a problem of browning, and this is caused by interaction between the high energy of electron beam produced by the cathode and of course the molecular structure of the glass itself on which the electrons are incidenting. Now, we have a table here showing the advantages, the strengths, and the disadvantages, the weaknesses of the CRT. As you can see on the left hand side, I have the advantages, which are more. They include high resolution, they are versatile addressing format, excellent image fidelity, high speed, high bandwidth, excellent contrast, good selection of phosphor, down to inexpensive, that is low cost for the production of that. While the disadvantages include the high power consumption, the weight of the glass, it is heavy, the size of the footprint, that is the size of the image, sometimes it is not as qualitative as we need, and of course the CRTs do emit electromagnetic radiation, and they require reparation from time to time. These are the disadvantages. So how do we select a CRT for a particular application? The 3 parameters that are paramount in selecting the design or the particular CRT for our application. Number one is resolution, number two is brightness, and the third one is the screen size. Whenever you need a very high resolution, so which are used, for example, in the medical imaging and in the film recording, so the CRT may use the designs that already exist for that purpose. And of course, whenever the brightness is your priority, there is a design for that. And of course, the screen size, which I told you, it ranges from 12 millimeters up to more than 1 meter diagonal size. So the CRT can be designed sometimes for customer specification. That is, if you want a CRT that is not existing in the market, you can give the manufacturers your specification and they can come up with the one that suits your application. So this is the end of today's lecture. Thank you very much. I advise you to watch over and over again as usual. Thank you till we meet in our lecture number 4.